Welcome back. In our last video, we came up with this, which is the correct formula that we're going to use for a confidence interval to estimate a population mean. We determined that we don't know sigma, the population standard deviation, which is why you see Sx up here. And it turns out, for reasons that we explained in the last video, that we can't use z star, the critical value from the normal distribution. We have to use t star. And so we've got a new critical value here, t star df, and we said that t star df is the critical value from the t distribution with n-1 degrees of freedom. And you don't know what most of that means yet. That's what this video is about. Here we're going to introduce what the t distribution is, what degrees of freedom are, and how it's different than the normal distribution that we're used to. So let's take a look at the normal distribution first before we talk about t. Here we go. So this, I don't know how big I need to be. There we go. This is the normal curve, all right? This is z. This is the formula for the normal distribution. You do not need to know that. That is beyond the scope of this course. For those who are in or have taken calculus, I'll tell you that if you go to graduate school in statistics, you're going to have to take the antiderivative of this, and that's not pretty. But in this course, it's just something to look at and be like, wow, that looks really complicated. That makes this shape awesome. Yeah, that's what happens. Okay. Specifically, what you see here in red is the standard normal curve, and that is where the mean of this curve, the axis of symmetry, is at 0, and the standard deviation is 1. Now, the standard normal curve has parameters 0 and 1, but remember, the normal curve in general can have any mean and any positive standard deviation. So we can take these sliders. By the way, this applet, there is a link to it under discussions, but know that I have changed some of the properties of the sliders a little bit, so it won't look exactly the same if you look at it, but you can mess around with this on your own from Canvas if you want. But we can change the mean. Right now it's 0, and I can move it. If I make the mean positive, it shifts the curve right. If I make it negative, it shifts to the left. Slide to the left, slide to the right. I can't crisscross on this though. Anyway, so we can move the mean and we can change the standard deviation. If we increase it from 1, the curve flattens out. The standard deviation gets bigger. That means you're going to have more area in the tails of the distribution. If I make it smaller than 1, it becomes taller and skinnier. There's not going to be a whole lot of area in these tails, the smaller the standard deviation is. But for the standard normal, mean is 0, standard deviation is 1. This is our curve. We have found that we need to use the t distribution for our new t star critical value. So how does the t curve compare to the normal curve? Okay, again, red is standard normal. I'm going to add a blue curve here, and that's going to show you what a t curve looks like. Okay, so let's see. I can get rid of myself here for just a sec. You can take a look and compare those two curves. You can see that the t curve, the blue one, has the same general shape as the standard normal. It's unimodal, it's symmetric, and it appears to be symmetric about the very center of the curve. It's got a similar shape, but the main difference in the t versus the standard normal is out here in the tails. Notice that the t curve, it is more gradual in its decrease there. There's more area in the tails of the t curve. And yes, I will say the formal term that statisticians use to describe this behavior is that the t curve has thick tails. It has thick tails. That's what we say. And it's true. There's more area in the tails of the t curve than in the normal. Why? Well, remember, when we try to use z star, which is the critical value based on the standard normal curve, if we wanted a 99% confidence interval, we would go out to, I think it was 2.576 or something like that. It's like out here somewhere, because to the right of that point here and to the left of negative 2.576, that's 1% of the area under this curve. But what we found when we used that z-star critical value is that the true confidence level that we saw was only about 92%. By using t-star instead with these thicker tails, if we go out to 2.576, we're going to see a lot more than just 0.5% on each side. If we want a 99% confidence interval and we use the t-curve, the blue one, we're going to need to go way further out and get a larger critical value to get that 1% of area on the ends and 99% in the middle. Okay, so what we said, if I can bring myself back here. Oh, not like that. I don't want that. Hold on. There we go. I was too big there for a minute. I said that in our formula, T star df is the critical value from the t distribution with n minus 1 degrees of freedom. So, the degrees of freedom are n minus 1. And it turns out that the t curve, the blue one, we can make it look different based on n, the sample size. So remember how we changed what the standard normal curve looked like by changing the mean or the standard deviation? Okay. The only thing that changes the t-curve, the blue one, is the sample size. Right? So what you're looking at right now is if the sample size is equal to 2. And that would reflect a degrees of freedom of 1. Degrees of freedom for right now. This will change. But right now, what degrees of freedom means is it's whatever the sample size is minus 1. The reason for that, I don't want to get too far into it. We'll talk more about it a little later in the course. But essentially, if you know the mean of a sample, say you're taking a sample size of 4, and you know what the sample mean is. How many of the individual values do you need to know before you can know what the rest are? If that makes sense. So you know the sample mean is 12. If you know one of the 4 values, do you know the rest? No. What if you know 2 values? You still don't know what the other 2 are. But if you know 3 of the 4 values and you know the sample mean, you can find out what the 4th one is. Right? You could just take the sample mean times 4 and subtract the 3 individual values to get the 4th one. So if you have a sample mean of 4, then there are only 3 of the 4 individual values that are free to be whatever they want. The 4th one is stuck being what it is. There are only 3 degrees of freedom when n is 4. If that makes a little bit of sense, I tried to explain it in a way that might make sense. I may have failed at that. But anyway, degrees of freedom for now is just n minus 1. So what you're seeing right now is the t curve where n is 2, which means the degrees of freedom is 1. That is the smallest value of both n and degrees of freedom that is defined for the t curve. Suppose n is just 1. You're taking a sample of 1, one thing. There would be no degrees of freedom. There is no standard deviation for a sample of size 1. It doesn't exist. Everything just falls apart and blows up. Okay, so n equals 2 is the smallest number, is the smallest sample size, and that represents degrees of freedom being 1. That's the smallest that it's defined for. If we change this n from 2 to something higher, this curve will change in the way it looks. So I want you to think, before I move the slider, I want you to think, how will this blue curve change if we increase n from 2 to 3? Which means we're increasing the degrees of freedom from 1 to 2. Increasing sample size, in general, means that the variability decreases. Right? So as we increase n, if I move this up to 3, the variability in this curve should decrease. What does that mean it's going to look like? How is it going to change? I know you're probably screaming, just do it! Just do it! Okay, fine, I'll do it. We're going to go from 2 to 3. Did you catch that? We went from 2 to 3. 2 to 3. 2 to 3. You see a subtle change in the tails. Take a look at this left tail. Just focus on the left tail, going from 2 to 3. 2 to 3. You see a slight decrease in how thick that tail is. Yes, it's funny every time I say it. We get less area in the tails, and if you focus more on the mean here, from 2 to 3, 2 to 3, it's getting higher. So by increasing the sample size, increasing degrees of freedom, we're taking that variability and we're smushing it so that it gets thinner and taller. It's becoming more attractive. And you might notice, if we're comparing it to the normal curve, the standard normal curve, it's becoming closer, right? The mean is getting closer, and the tails are getting thinner, kind of like the normal curve. So let's keep increasing n, increasing the degrees of freedom, and seeing if that continues. 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, we're at n equals 41 at this point. There's not a whole lot of difference between those curves now, is there? You can see still there's a small difference in the tails. The blue is still a little higher than the red. Those tails for the T curve are still a little thicker with n equals 41, which means degrees of freedom is 40. We can even go up to 50 here. And there is still a difference, but it's very small. You can see that as n and the degrees of freedom increase, the T curve approaches the standard normal curve. And in fact, if we had a slider that went all the way up to infinity for n, the T curve would become the standard normal curve. So for high sample sizes, using T and using the normal curve, you're going to get almost exactly the same results. So why do we even need this T distribution if it's so close to normal? Well, for high sample sizes, it's very close. But recall where we started. We started with n equals 4 in our example, which means degrees of freedom was 3. This is a sizable difference in the two curves. And we saw that when we tried to use method 2 for the confidence interval, where we used S, but with Z star, and the confidence just was not there. We wanted 99%, but we only had 92%. That's why we need the T distribution. That's why we need the T curve. But it's important for you to understand what the T curve looks like, how it behaves, and how the number of degrees of freedom, or the sample size, affects what that T curve looks like. As your n and degrees of freedom increase, the T curve approaches the standard normal. Okay? So that's mainly what we are seeing here. The T distribution is very similar to the normal curve. The main difference is it's got those thick tails. And that accounts for the uncertainty of us not knowing what sigma is. When we're estimating sigma with S, we have to give ourselves a little bit more room for error, and that's what those thicker tails of the T curve allow us to do. Okay, we're back to the board here for the end of the video, where we're just recapping what we figured out from looking at that applet. When we use S, the sample standard deviation, to estimate sigma, the population standard deviation, in inference procedures concerning the population mean mu, and by inference procedures I mean calculating confidence intervals or conducting hypothesis tests. We'll get to both of those in the next few videos. When we have to use S to estimate sigma, we're going to be using the T degrees of freedom family of distributions. Okay, that's when we use the T distribution. So these distributions differ from the standard normal distribution only in that T has more area in the tails. It has thicker tails. And that allows us to account for the uncertainty of not knowing sigma and using S instead. Degrees of freedom, df, is equal to n minus 1. N still represents the sample size, at least for now. All right. So in an example, and we'll look at an example in the next video, if you've got a sample of size 20, you know you'll be using the t distribution with 19 degrees of freedom. As the degrees of freedom increases, as we move that slider up in that applet, which means that the sample size is increasing as well, that t curve, those t distributions, lose area in their tails and become more like the standard normal curve, right? And at high levels of degrees of freedom, we're talking like 50 and above, right? Especially if you're in like the hundreds. Those two distributions are virtually identical. Okay. They are still different, and the differences are important because we're going to find that the conditions we need to check to use the t distribution are not the same as the ones we use for normal. There are going to be some differences in those conditions. So just because they're very similar doesn't mean they're interchangeable. They will have different conditions. And it turns out, a little bit of a spoiler here, it's going to be easier to meet the conditions to use the t distribution than it was to meet the normal distribution. So that's another reason that t is good. Not only does it give us accurate confidence intervals, but we're going to be able to use it in more scenarios than we were using the normal curve. I think before we come to working out an example where we use the t distribution, it's important to note the differences in what we've learned in the past and what we're now doing. So back in the past, we assumed that we knew the population standard deviation. We knew what sigma was when we first introduced the sampling distribution of x bar. If we know sigma, that sampling distribution of x bar is approximately normal in shape with a mean of mu and a standard deviation of sigma over the square root of n, right? Assuming that the conditions are met that we've checked. This allows us to use the normal distribution to calculate probabilities. So we did that back in the day. We're like, okay, if you take a sample of size 6 with this mean and this standard deviation from the population, what is the probability that the sample mean is less than 4, right? You would use this sampling distribution and you would use the normal curve to calculate that probability. You would do probability that z is whatever, okay? But in general, we are not going to know sigma. If sigma is unknown, which is where we're operating now, we must estimate it with the sample standard deviation, Sx. That means we are going to be using the standard error of the sampling distribution of x bar. This is the true standard deviation of the sampling distribution. But if we don't know sigma, we have to plug in S. That makes it the standard error. Okay? And that means, if we're doing that, we can't use the normal distribution anymore. We've got to use t. And we're going to be doing this to determine critical values, which means now we're using t star for confidence intervals. And when we get to hypothesis tests, by estimating sigma with S, we're going to have to calculate a new test statistic t instead of z that we did for proportions. Okay? So, the switch from normal to t is only happening because we are estimating sigma with S. We can no longer use the normal curve anymore. That's when we use t. So the reason for these last two videos is to set up this. A one sample t interval for a population mean has this formula that we discovered earlier. And now we know why it is this formula. We have to use Sx because we don't know sigma. And now we know if we do that and we're using the standard error here, we now have to use the t critical value not z. So this is a t interval, not a z interval. And it's for a population mean. And this t star df, that's the critical value from the t distribution with however many degrees of freedom you've got for a given confidence level. We will get into an example where we calculate a one sample t interval in that next video. So I hope you're excited. Now you know all the background. This was all the theory behind it. I could have just given you this formula and then gone through how to use it, but I feel like it's so much more powerful and it's so much more likely to stick. Why this is the way it is by going through it. And it only took a couple of videos, so there you go. So we're going to go ahead and start calculating these intervals starting in the next video. As we've said, we're also going to be using the t distribution for hypothesis tests for a population mean. We'll see how that goes. And then even further on, we'll extend that to two means. How do you find a confidence interval for the difference in two means? Or a hypothesis test for a difference in two means. What we found in Unit 6 when we dealt with proportions, a lot of that will carry over. And you're already seeing that here. The basic construction of this confidence interval is still statistic plus or minus critical value times standard error of the statistic. That's going to keep happening. We've got a new distribution, yes, things are a little different, but the bones are still the same. I hope that that gives you hope as we go along, that we're not starting over. We're just tweaking some things. So we'll calculate a confidence interval next time, and we'll see you there. Take care.